So let me pull up the screen here. I went ahead and created the project on Circuit Maker and got our first sheet of the schematic up. There's a long way to go from here. So let me go ahead and pull up my diagram here. All right, so here's our circuit board diagram. All right, so we got all this stuff, and tonight I'm going to start with the power supply. So USB-C port, kind of. Maybe that'll include that. So the voltage booster, the circuit and chip for recharging, and then the regulator on the other side, and then all the connectors for the batteries themselves. This should be good. Let's see, what else? Yeah, so that'll be a good start. So I'm going to try and separate this out and organize it. So I'm going to have different sheets of the schematic, like different pages for the schematic. And the first page will be this power supply. Then maybe the next page will be like the buttons. And let's see, we would probably want to do LE interactive stuff. So buttons, screen, speaker, anything that gives data back or receives data from the user. And then maybe like the TNC itself is a thing. And then all the NeoPixels is a thing. And then accelerometer and motor is a thing. So we'll see. We'll separate things out too if they start to get really complicated. We'll make multiple pages for it. So I'm just going to follow this. So far what we've really done to decide this is make this block diagram and pick out components that we want to use for these different blocks. So now we have to go through and actually create each block and all of its intricate little parts. As a standard rule, we're going to be using for capacitors and resistors and things like that, we're going to be using what's known as 0805 components. It's just a size that will be fairly easy to work with without using that I can use with a standard soldering iron and not have to use an oven or a microscope or anything. And then everything else, yeah, we'll just use it. And so each one of these chips, for example, like this recharge circuit, each one of these has its own kind of like has its own data sheet with its own application circuit like laid out. It tells you exactly how to use it, what parts you should use around it, what's expected to be part and how the circuit is supposed to be. And in some cases, even tells you how the PCB is supposed to be laid out around that specific component. So certain things like the driver for this motor and maybe the voltage regulator, because they push a lot of power and get hot, you have to put a ground plane in there in a certain configuration to pull that heat away. And then other sensitive things like this recharge circuit, it may expect like certain traces to be short and certain ones to be longer and whatnot. Certain capacitors to be in close proximity to the chip, while others can be farther away, that kind of stuff. So we'll go through all of that one data sheet at a time and figure out how to do it. All right, I guess we'll start with the voltage boost chip. So that is this. I'll do my best here. We're going to be looking at a lot of data sheets now that I'm thinking about it. Oh. Okay. I should probably save these somewhere maybe so I can have them. All right, here we go. So first things first, pull this up real quick. So here's example, it gives a schematic, right? Okay. So we'll have to go through and figure out exactly how to do this. 12 volt output boost converter with external bias. Is it always 12 volts? Did we decide that, or is that just a one option? Output voltage 12. It is always 12. Okay. For best accuracy, R2 should be smaller than 100 microvolts to ensure the current flowing through R2 is at least 100 times larger than the FB leakage. The lower value increases the immunity against noise injection. Changing it to a higher value reduces the amount, so it gives it higher efficiency. Here's all the equations to work out different things. "14-volt boost converter." Well, we probably don't need that. Oh, look, it gives the actual PCB layout as well. So, awesome. That is exactly what we want. Okay. Output voltage is up to 14 volts. I thought it was adjustable. I thought that was why we picked this one, but maybe not. All right, well, we obviously need these components. We'll have to go through and double check everything, make sure that it doesn't want like a specific size or something. All right. Part. All parts. Search. I wonder what is the chances that this has already been made. I'm just going to search. I'm just curious. It's not looking good. Lots of toggle switches. 61048. Ah, nothing. All right, we're going to make a custom part. All right, well. What is the one we picked out? Oh, 48. What is the DBVT? I need to double check. All right. DBVT. Oh, okay. It's just the packaging. So we can probably just say this then. And then one more thing, now that I've realized that. Okay. Here's this thing again. I want to see V out, V reference. R1 minus 1 times 2. Output voltage is programmed via external resistor divider. External resistor divider R1, R2 is shown in equation 1. The output voltage is programmed to the desired value. When the output voltage is regulated, the typical voltage is 100 millivolts. Okay. So yeah, we can adjust this voltage. And this is giving you the values you should use for like 12 volts, right? Because effectively you're making your own voltage divider to do this. Okay. This is already looking better. So I guess, should we go for 8.4 volts? Because that's what the batteries are charging to. I mean, we can always change it later if it needs to be higher. Microhenries. Okay. And this is going to have to be... So this is to help stabilize the power. What are these two things? With external bias. Hold on. Thought I saw more basic. Right, this one. Okay. This is the one we probably want. All right, so double checking that. I was worried that, because I saw the 12 volt and 14 volt thing, that it mattered. Adjustable, we call this. How about a non-synchronous boost converter? I'm just using the words that they use here. Okay. So another thing too, Circuit Maker did a major update between the last project and this one, and it's completely yeah, it's different, right? So this is gonna take some work. All right, new symbol, and we're drawing a symbol. So this is just, we'll just use the one given right here. We'll just basically make this, but add pin numbers as well. Okay. So, I guess we start with a rectangle. Okay, clearly I don't understand how this rectangle drawing tool works. Back up. Really? Okay, thank you. Here we go. And then I'll probably make this a little bigger. I'm not a good judge of how big this is going to be on the schematic too. 200 mil, 300 mil. So up 500 mil, down 500 mil. So on the page, it's about an inch tall. That's probably fine. That'd be sizable. Does it connect on that side or this side? I think this way? I don't know why it's starting at there. Oops. How do I rotate it? Nope. Okay. And then, whoops. One and one. Oh, the designator needs to be... Right. Which one is this? So the designator is the one there. Okay. The name is the one that needs to be needs to change. So that's VN. This is ground. And this is enable. Active high. I wonder if that's supposed to have a pull down on it. It doesn't show it here, but we might do that. All right. Which one is this? Oh, pin 6. Which I think is SW. Oh, what? The, All right, the schematic is completely different from the actual package, so we're gonna have to go through and renumber these pins, but we can do that. SW. I want to have them in the same way that they are in the schematic here, because I think that is probably done very specifically to help it make it easier to draw on the schematic. See, okay. And then FB. All right, and then we're gonna have to renumber these. Give me just a sec. So SW is 1. Ground is 2. So that's right. FB is 3. This is gonna be so confusing. EN is 4. Enables 4. Five is VN. And I guess that leaves frequency for 6. Okay. Do we need like a name or something? I don't know how to do that. We'll save this for now. We might have to come in and change it later. All right. And then we need a footprint. This is going to be the trickier of the two. Ooh, excuse me. Okay. We probably just want to do the pads. It gives us a recommended like circuit here, this thing. But there's really no point in doing any of this extra stuff. We'll do all that later with the extra components. So we'll just start with just placing these specific pads for it to mount to. Here we go. And so in the data sheet, you can see here, there's a footprint provided, which tells you exactly how to do the whole layout. So excellent. Okay, so how do I place pads? I'm gonna have to learn all this stuff again. I've completely forgotten it since we did it. Assuming pads. Oh, this one. That's what I want. Right, and I really don't want that. Does this have to be a via? Multi-layer. Solder? Interesting. I just need to see everything that's going on here, and then I'll work it out. In the meantime, let me know how your Thursday's going. I have these Dogecoin bounties available. I'm glad they're up here. For a second, I panicked and thought that I had just had the webcam on the whole time and nothing else. So, if you want Dogecoin, there's some bounties available. Okay. Rectangular. Said top solder. Top solder is what? That's the one I picked, but that might not be the right. Top overlay, bottom layer. It should be top layer, shouldn't it? Yeah, this one. I think it should be that. But there should be a stop as well. Okay. Hopefully, what are these in? What units are these in? I guarantee that whatever unit I'm using, it's going to be in the opposite one. It looks like they're using millimeters. Yep. And I'm using mils. Typical. All right. Let's see if we can change this. Board, inspector, library, shortcuts. Oh, here it is. Let's go metric. There we go. Okay. So it is 1.1 millimeters wide and 6 millimeters tall. Or 0.6, sorry. This is still going to be hard to work with. Okay. And then all this stuff is done as an offset from the center in this data sheet, which is awesome because it actually makes it easy to do. Sort of. So this should be negative 1.3. And then it should go up 0.95. So we're pretty close already. Okay. So that's the first one. Then we need multiple. Oh, there it is. Let's make sure we don't have that. All right. Okay, so the Y should be 0. And this should be negative 1.3 again. There it is. Okay. Ah. Slowly learning this software. It's neat software. It just requires a lot of work. All right. So negative 1.3 millimeters and then negative 0.95. I just realized that I made this one too high. This should be positive 0.95. There we go. All right. 1.3, 0.95. Zero. All right. As I get the hang of this again, I'll go faster to 0.3 or negative, positive 1.3 and negative 0.95. All right. So that's everything together there. Now we need to rename designator 2. Three, 4, 5, 6. Okay. Mask opening, exposed metal, yada yada yada. All right. Let's see if it has exactly that. Paste mask expansion, solder mask expansion. Manual. So it looks like 0.07 is the distance around. Let's see if this works. Okay. Oh, it does. Okay, so I am theoretically doing this correctly. So that's the distance between the stop, like the top layer where they want it to stop and then where the metal starts. So I don't think it really matters that much, but since they bothered to specify it, I am going to specify it as well. Interesting stuff. It's very interesting to me. I'm gonna try that again. It's very interesting to me to see what kind of stuff people bother to outline in their data sheets. Like companies that are, like this is a TI part. TI is huge. Texas Instruments. They make all kinds of chips, and they're based here in the U.S. and they've been around for so long that they have so many standards for how their products are set up and what they define and everything. And their data sheets reflect that. There is a lot of things defined. In a lot of products like this, you would see like this defined, the pad size and then the spacing of the pads, but they wouldn't necessarily say, oh, there should be this much space between where the metal is and then the covering layer, the stop layer is. The fact that they bother to spec all of this out is incredible. Molex is the same way. It's another great example. Molex makes connectors, and their connectors they define everything. But then if you go to another company that's much smaller or less known about, there may be a lot of things that they leave out of their drawings and stuff like that, or about their reliability specs. So you can tell how rigid a company is, and what I don't know. You can just it gives you an idea of kind of like what the effort they put into something, and maybe even their customers as well, because the people that tend to buy TI parts and spend the extra money are people that care about all of these things being defined. Okay, so the paste is given as well. That other thing there, I don't know. 6.21. It's the exact same as the pads. Okay, so this default of 0 millimeters is correct. All right, so that's all of the pads. Now let's draw, like, whoops. I want to draw the part, like where it's going to be. So we can have kind of a drawing on the board for like keep out purposes. Okay. So the part is, the actual like casing is 1.75 millimeters wide at its max. Its smallest is 1.45. They also spec out the tolerance because that can vary. And then 3.05 tall. So let me get a calculator. Now we get to do all the fun math. So let's just draw a couple lines and then we'll position them accordingly. Ah, yes, these are in the copper layer. Probably not what you want. We'll just move this to the top overlay. Notice too how there's given top and bottom options here. You can create parts that have definitions on multiple layers. So that's kind of cool. So yeah, okay, we want the top overlay. And then our start is going to be, what's 1.75 divided by 2, 0.875. That's negative 0.875 and positive 0.875. And then our maximum height is 3.05, so that's divided by 2, 1.525. Okay, so that's where we want it. Same thing here. Top overlay. And then this will be the negative 1.525. And then we said 875. Excellent. Okay, so that definitely looks much better. Then we'll want like a dot or something here to denote that this is pin 1. Another way we can do this is put a line on this side. Actually, that's what I'm going to do. I kind of like that better because it'll be hidden underneath the chip. So we'll put a line here to here. Oops. All right. And we will say that this is the top overlay, and then where it's at might be okay. Actually, we'll adjust the height a little bit. Yep, dead even. All right. I didn't even bother to look at the thickness to see if that was anything I cared about. Width 0.254, so that's a tenth of an inch. I think that's kind of big. 254 millimeters, 2 inches, 0.01 inches. Oh, okay, 1/100 of an inch. I feel like that's kind of thin. Well, 10 mils. Nah, that's probably good. We'll go with that. It's pretty standard. All right. What are the other options here? Fill, solo, via, keep out. Interesting. Text. Big text. I don't know why it defaults all this stuff to the... Oh, because I'm selected... Hold on. I'm selected that layer, so... I don't know how to say that text is like the name or something. The text should be something like U question mark, I guess. It probably needs to be way smaller too. Text height. No, it don't have to be sizable. Probably like 2 millimeters. I know that looks huge, but that actually is correct. Also, I don't know if voltage regulators are U's. Hold on, let's go look at the Wikipedia article. Okay. So these are called designators, reference designators. Basically, everything on a PCB should be a letter followed by the number of which version it is. And here is the Wikipedia article on how exactly, what exactly you should use. So U means integrated circuit, or IC, or chip, basically, right? If you're doing vacuum tubes, for some reason, V. But then there's some that are pretty obvious, like resistors. Resistors are R. Others that are not so obvious. What's a good example of that? Oh, oscillator, yeah. Crystal or oscillator is Y or Xtel. So, you know. So either voltage regulator, but this is a boost converter. I don't think there is a thing for boost, but a voltage regulator might be pretty close. So we may want to say VR. And then I'm going to look up something real quick. Okay. Oh, interesting. Okay, so you do put a question mark, and then it, when you run a certain process, it auto numbers it. Okay, so we want a question mark, definitely. VR, I love this giant text for this tiny little part. I picked out this part because I thought I might be able to solder it by hand, and now that I'm looking at it, I'm not feeling so good about that, so we'll see. I might have to get a little creative, or buy something to help me with that. Okay, so this is our pad, and I think this is good. I don't think we want anything else here. So let's save this. And then go here, save this. We probably want to actually change this. We need to add the 3D model. So here, if we look at the 3D body. Oh, that's to add one. Hold on. Nope. There it is. Thank you. We can see the 3D model is not great. Also, it's really hard to see in this. Jeez. Can I change the background? There should be a way to set colors. Schematic, PCB editor, display. Change the colors of the layers, but oh wow, you can have tons of layers. That's awesome. And Circuit Maker allows up to 32 layers, it looks like. That's really awesome, actually. Well, that would be fun to work with. Okay. I don't know if this is going to get us anywhere. We'll just close it. And just accept the fact that we're not going to be able to see this very well. So I need to make the part like sticking up somehow. So that we know where it is. So 3D body. So let's go back to this. Right. Okay, that wasn't what I wanted to do at all. All right, let's try this. Okay. All right. Extruded, yada, 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 center. How do I say how big it is? 2. I remember this being really hard with the last one too. All right, well, we'll say that it's probably correct, right? Because it goes to the middle of each of those, yeah. I need to learn how to do this better. All right. Overall height, 0.254, standoff height. Extruded, cylinder, sphere. We just want to extrude a little bit. How tall is it? Off the board. 1.45 millimeters. So that's what we'll do. Okay. I think that worked. If I go to 3D view, hey, there it is. Look at that giant thing. Interesting. Okay, yeah. So that's definitely the highest off the... And then I probably could go through and put like the pins or something, but I don't think that's really necessary here. Just having this will be enough for us to denote where it is. Okay. So that looks good, and then go out here, and I know it's hard to see those letterings, the letters, but it all looks good. So save that, and then if we go here, all right, it shows up. The part exists. And it looks like it already has, oh, okay, by default, does it do the name and symbol? Because if it does, that's good. I wonder if there's a way I can link those. All right. So now that this is made, how do I commit? So if I go here now to this and add a part, can I find this? TL V I just realized when I was searching for it, I didn't search TLV, so I might have just made something that already exists. 61048. Oh, it does exist. I spent all that time making it. It already. All right. Well. I'm doing great. Hopefully, it's a good thing I'm not recording this, right? Documenting my failures for forever. All right, hopefully nobody makes fun of me too much for that one. So I guess now I forgot which one we're using, the T. All right, so we're using this one. So now after all that, I can just go ahead and place this part. Part URL. Wow, they did the model the exact same way I did. All right. Every time I click on this, it opens up the page over here. Can I place it? There we go. Thank you. All right, so how are we laying this out? I guess up here, power coming in. All right. U1. So they went for the U designation. All right. I don't know what that error is. Other than it may be just a disconnect error or something. All right, well, knowing that's a thing, it might make this a little easier then. We still have to go through and find components for it all. Yeah, let's start with that. Move this down a bit. Okay. All right, so let's see. Let's do a wire. And then I hate where this text is on this thing. Can I move this? Yeah, that's awesome. Okay. Net label. And then this is going to be USB. We'll just say 5V. Okay. I like the underscore. Okay, well, let's find this part again. All right, so here's what I'm going to be looking at. We got to add all these components. This capacitor, this inductor, these two resistors, this capacitor, and this diode. It should have either recommended values or a way to calculate them for most things. So here it gives an example of values. This is with the bias. I don't really care about that much. I'd just rather do the simplified. Just wish it would give us values for this. Simplified version. Oh well. So we'll have to choose capacitors as well. And other things. So and then I'll have to figure out if it wants a specific type of capacitor. Oh, they recommend some. I bet both of these are tiny, though. $1206 part. I feel like that's fairly sizable, actually. .2 millimeters by 1.6 millimeters. Yeah, that's a pretty big part. Okay, I like that one. Let's see if it exists here. Yep, looks like it does. Oh, but I don't know if it doesn't have any models. Of course it doesn't. And I'm going to have to start putting together a spreadsheet of all of these parts because this is going to get complicated in a hurry. Man. Oh, these are expensive too. Jeez. I just realized that. All right, well. Oh, excuse me. Let me find something similar. At least this gave us a pretty good idea of what we should find. I'd probably just use any ceramic cap. Oh, come on. I wonder if it makes sense to make a model. Oh. Hold on. Just trying to think of how I did this. Last time I didn't have that many components, so this wasn't that complicated. I could just pick a few things and it was easy to keep straight. But this is going to be really hard to keep straight if I don't get it exactly right. So let me see here. I got DigiKey pulled up here. Let me just search for something like this that's not incredibly expensive. And then, because these are like $1 each. And that'll get, if we keep buying parts like that, it's going to get to be a lot. But we'll get something very similar. Let's see. Let me pull this up. All right, let's just go ceramic capacitors. Okay. What was this? They suggested a 1206 package, which I think is fine actually, because that's pretty big. So in stock. Let's go active. Make sure that they're currently being sold. Capacitance, we want 10 microfarads. It may not matter how much money we want to spend. This might be a pretty expensive thing, no matter what. Yeah, these are fairly pricey, no matter what kind you get. All right. X5R, temperature coefficient. And do we have a tolerance plus or minus 10%? All right, we're zooming in. We want cut tape, so I don't have to buy a bunch. Just want to buy a couple. Samsung Electromechanics. 6.3. Oh, these need to be 20. I think it said 25 volt. Yeah, just in case. And there's the one we just looked at. Here we go. This one. This is a good drop-in replacement, and it's cheap. And I like cheap. All right, let's see if we can find this in here then. If not, we'll be using something or making something. Yep, and it does, and it has a model. Great. I like that. And I'm going to have to start getting rid of these part names for non-ICs and things like that, or this is going to get really complicated. Okay. Let me pull up this. This is the PCBA bill of materials. And I'm basically just going to start labeling things out as we get them. All right, let me reorganize this a bit. I'm going to want this top line. Let's see, location, description, manufacturing part number. So 1. I don't know if I should add a manufacturer in. I don't think that's that necessary. All right, description. I'm going to have to format this whole column to wrap. There we go. So this way I can put all this stuff up on the GitHub too, and anybody can go look at it or use it. Okay. So now that I got this made, I really need to find a way to rotate this like on the fly. All right, properties. $90. Okay, and then where is the schematic here? All right. Wow. Okay. All right. So that's not actually going to be connected to anything anyway, because it still needs to go through a diode and such. But the voltage divider will go right here. Okay, cool. So let's see if we can find a recommendation for the diode. Because they recommend inductors and capacitors. I don't know if they recommend a diode, though. Okay, here we go. Oh, they give an example of one they recommend. Perfect. That's a pretty big part. So they recommend this one in the data sheet. 42 cents each. Yep, I can get behind that. Let's see. Oh, there's 0 in stock. Cool. Probably not any plans to order, too. Mouser, maybe? Oh, they've got some on order. They're expected. Well, let's see if it's even a part I can get. Yeah, it is. Okay. Mouser's expected to get a bunch on July 28th. Which is fine. I don't think we're definitely not going to order it by then. I'm just worried about picking apart and then having it be like out of stock completely when we go to buy it. Like just not have a place to go get it. There's other places we could go. Possibly Arrow. No stock available. I don't know about picking this part. I wouldn't mind, but it just doesn't seem like there's a lot of them out there. All right, let's see if we can find a similar one. Oh, that's not the page I wanted. All right. Diodes. Single diodes. The single thing reminded there's something like also kind of cool if you're doing a lot of resistors at the same values and stuff like that. You can buy these packs. They're basically it'll be like 4 or 8 resistors in one component, and that has a bunch of pins in and out on both sides. You can drop it down, and then you can only place one part, but add like 4 resistors if you need it. Okay, so let's just try and find something similar. In stock, active. Okay. We need a Schottky diode. Diode type, Schottky. Okay. Voltage 20. That's what the one they picked. We definitely need to pick something that's easy to solder as well, so yeah. All right. Let's go for 1 amp here. This will make things semi-tricky. This one looks good. Forward voltage max drop. What is their voltage drop? 500 millivolts. Okay. Yeah. That's fine. Reverse leakage is a little high, but we're not going to have to worry that much about it. All right, I like it. I like this one. And there's plenty in stock, which is what I like even more. So let's see if this has an option in Circuit Maker. Ah, there's no sim part. Arr. All right, let's look for another. Obviously, I can make a part, but I really don't want to do that if I can avoid it. That was that one. I'm picking them based on how easy I think they'll be to solder. Obviously, these ones with that are underneath, not so easy, but with the tabs sticking out, they are actually, so. Yeah, 500 millivolts, 200 microamps. Okay, I think this could work. Let's see if these guys are stuff in Circuit Maker. I don't know what determines, like, for Circuit Maker, like, what parts they include, which ones have models. That isn't a model either. That kind of stuff. If it's just until somebody takes the time to do it, maybe. $0.09. That's really cheap, actually. Don't know how I feel about that one. On Semiconductor, kind of like their stuff. Let's try it. That's actually closer to the original spec too, as far as the capacitance and everything. So, all right. Yeah, nothing's got a model. Except that one that the original one, that was hard to find. A lot of options. Now I'm just getting curious, like to what level stuff exists in Circuit Maker. I wonder if they're just using a database from one of these suppliers and just include, yeah, they do, they have it. Okay, include everything, but not necessarily have a model of everything. All right, I'm gonna start going through this, seeing what exists. Need the manufacturer part number, please. Ooh, there's a model. What does this look like? So, there's 1 amp, leakage current, 1 milliamp. Ooh, that's kind of high. But the voltage drop is low. All All right, I'll try it. Why not? There we go. And then let me add that to the spreadsheet. This is going to take a long time. And I'm excited for every minute of it. All right. Description. Manufacturer part number. And a link. I should have a value column, honestly. That might help later. In case I like have to get like resistors at the same value or something, rather than picking the recommended one, I could just pick another one of the same because that would help save money too. So this is 10 farads. All right, and obviously this doesn't have a value. Okay. Cool. And then on our schematic, let me find it. I hope I didn't close it. I think I closed it. Uh-oh. Well, that's a shame. Let's open up that data sheet again. All right. D1 goes directly out, nothing between that. Part. There we go. And then I'm going to delete this. I don't think this is necessary. How do I hide this? Hide that. Awesome. Thank you. This too. I don't want the comment. Okay. Can I show a value? I feel like that would be useful. Is that not an option? Because that's really annoying otherwise. Interesting. Okay. Nope. Don't want that one. Ground. All right, let's go ahead and start connecting things up. Come on. I think it froze. Yep. If it crashed, that's going to be awesome. Just a bit of lag. Yeah, something definitely crashed. Because none of my windows are opening now. Oh, some of them are. Okay. Oh, all objects. I forgot. This is... Okay. I forgot about that with Altium. It's just weird that way. You can basically turn it off so that it hides any like windows you pull up or whatever. Which is an odd design choice, personally. AV4, so 8.4 volts. Okay. Let's connect these to ground. All right. So it looks like in the simplified one, the frequency line is disconnected. Actually, it is in a lot of cases here. Why is that? Odd. Okay. Oh. I'm not sure what that's used for then. Look at the pin out here real quick. Frequency. Frequency select pin. The device operates at 600 kilohertz if it's left floating or pulled high, and at 1 megahertz if connected to ground. Interesting. We'll leave it floating then, because I guess that's the default. All right, next step of this, the voltage divider. And math. All right. I'm sure it gives us an equation here somewhere, but I'm sure it's a very basic voltage divider equation. All right, V out divided by V reference minus 1 times R2 gives you R1. So select one, and then you get the other. Okay. So pull up the calculator here. So for our V out, we want 8.4. We divide that by the V reference, which I believe is 800 millivolts. So 0.8 equals 10.5 minus 1 equals 9.5. That should be the ratio between, so R1 equals 9.5 times R2. R2 being the lower resistor, the one connected to ground, R1 being the one between SW and FB. So, in the example they give here, R1 is, wait, do they have this backwards? I think they do. I think their equation doesn't match their schematic. Oh, no, wait, yes it does. Okay, yeah, sorry, I'm having a moment. Okay, so it's 1.5 mega ohms for R1. Maybe we assume that 1.5 mega ohms divided by that, and we should get our other resistors. So 1.5, well, here. Let's do 9.5 and store that, because we're going to need that for later. And then, let's see, 1.5 divided by this gives us 0.157, so 157 kilo ohms. Is that an easily available part? Surface mount chip resistors, 825,000 different products to pick from. That should be easy enough. All right, values. Let's just start with that. Wow, there's some oddly specific values here. What we say, 157 kilo ohms? What's the closest we can get? Probably like 150, right? Yeah, 150, 152, 154, 156. If we got a smaller one, it would actually make the voltage slightly higher, which would probably be a good thing, considering the voltage drop on the diode. So maybe a 156 would be ideal. How many parts? 1. Okay, that's not a common value. Looks like 154 is a common value. So we'll do that. Okay. So if we do 154 times 9.5 equals 1.463 mega ohms. We can get 1.47. And that's semi-common as well, so... Okay. Or 1.5. We really just want to make this easy. Yeah. So let's do 1.5 and mega ohms and 154 kilo ohms. And what voltage output does that give us? So, according to the math, so 1,463 divided by 154 equals 9.5 plus 1 times 0.8 equals 8.4 volts. Okay, perfect. Those are great values then. So 154 and 1.5 mega ohms. I think is what we did there. Oh, no, we did the 1463. No. We need to do 1.5. Sorry. 1,500 divided by 154 equals 9.75. Or plus 1 times 0.8, 8.59 volts. With the voltage drop, that's actually, yeah, okay, pretty reasonable. All right. So that's what we're doing. So 1.5 mega ohms and 154 kilo ohms. So let's find a resistor. Well, there's a lot of options. Let's pick a package size. How about 0805? Oh, excuse me. Oh, wow, and it has a model already. Look at that. All right, we're using this one. All right. Let's go ahead and place this. Thank you. I'll drop this here. And then there's plenty of these in stock. I think, yep. Yeah, 40,000 in stock. All right, and then which one is this? This is R1. Value 154K. All right. All right, that one's good. And then we need to find the 1.5 mega ohm one. Okay. Should be a few of them. $26. That'll work. What are our package size options? Oh, there's 26 that are 0805. Okay, good. Let's get a cheap one. How about this one? I found it. This is the same company, Panasonic. So maybe it'll have a part as well. And it does. Fantastic. Okay. Perfect. And there's 27,000 in stock, so there'll probably be more later. All right. And this should be R2, right? Yep. Okay, and then description, part number, and let's get a link. All right, that looks good. Properties, resistance. Oh, can we show this? Oh, it does show it. Nice. Wish that format could be better. Mega ohms. Nice. I didn't realize. Okay, that's how you do that. Hide the description. Good to know. So can I do that here? It doesn't have a thing for it. What happens if I check all these? Oh wow, it just throws all that crap on there. It says show more, so maybe it does have it. Manufacturer part number. Typical. Okay, I probably can add a value in there. So I might do that. Let's do this first though. Properties, hide that. Wow, this has a ton. Geez. Resistance. We're going to change this to 4 kilo ohms. I like to have the resistances on the schematic. It just makes things easier to understand, like why you're doing things a certain way and whatnot. Okay, just move this down one. There we go. And let's do some wires. There we go. I guess this ground isn't really that necessary. I'm just going to do a wire. All right. Frequency we leave floating. Enable. Where does that go? So pulling our schematic back up. Oh, we still need to do this one VN. All right, so enable. Off is low, on is high. So we probably want to tie that high. Might have to use a divider for that. Unless the chip can tolerate up to 5 volts coming in. So let me see here. We need to find out what the enable tolerance or values are, minimum values. Voltage enable, logic high 1.2 volts, logic low 0.4 volts. Is there a max? Begin. Maybe not. Weird that it only found, okay. I'm assuming it can tolerate up to 5.5 volts on that enable pin. So we could probably just tie it to that. And put it on a pull down maybe. Do like a 1 mega ohm resistor. Because I don't see anything else. Enable pull down resistor. Oh, this must be internal. I think. So we might not have to, because it might have its own pull down resistor inside. That would be ideal. Okay. Yeah, so you just connect it to straight to that. All right, that gets connected to power. All of that to figure that out. There we go. All right, and then we have one other thing that has to get done. See, I'm gonna move this down over here. Okay, we need a bypass cap. It probably hasn't, I don't know if they would define like what this one should be. This is probably just a generic. I just need to know the value. I think they expect, okay, 1 microfarad it looks like. All right, 1 microfarad's easy. Let's do that. Double check if there's any recommended stuff. Yeah, they say 1 microfarad. Input and output capacitor selection. They recommend output capacitors, but for the input, yeah, I don't think it matters that much as long as we get something that can handle the voltage and everything. Okay. Let's go find a capacitor. Maybe by the time this stream is done, we'll have figured out this one part, which will have given us one block of our entire diagram. Oh man, this is going to take a long time. Ceramic capacitors. 677,000 options. Only 40,000 are in stock. All right, what we say, 1 microfarad. Voltage rated needs to be higher than 4. Probably anything up above that's fine though. Tolerance probably doesn't have to be that tolerant either. We do want an easy to work with component though, so 0805 as usual. Might as well go for the same temperature coefficient as the other one. that really doesn't matter that much in the sum of stuff. So, all right. Good luck. Let's pick one that is already in Circuit Maker. Let's see if we can find a cheap one, actually. Wait, did I click the wrong capacitance? I meant to click 1 microfarad. I think I clicked 0.1. That would make this a little tricky. 1 microfarad. Plenty of options. All right. Well, let's start with... Let's just start going down the list. Nope. What about AVX? Could they possibly have... They do have a model. Nice. Okay. That's getting placed. Okay, let's rotate this 90. And then let's show the capacitance. Hide that. Relabel this. 1 microfarad. Okay. And then I'll put this right like here. Wow, I'm just running out of room to put this big line of text. Let me just change this. I want to take out the Texas Instruments part. Just have the part number. Okay, and then just drop that right there. Perfect. All right, wires. Oops. All. Create a wire. Go, and that's going to go here. Excellent. All right, last thing. We need an inductor up top for something, some sort of feedback or something. You know, it's come to my attention with this, with the inductor at once here. Maybe this. I wonder if this part does not work the way I think it does. Because I'm worried that inductor would effectively create a short if the current's not changing, so the current must have to change, or the voltage must have to change. Interesting. Inductor current. SW. Oh, interesting. Okay. So V out's on the other side of that diode, and with the way this is going, making pulses. Okay. Effectively like a switching regulator. I mean, which, yeah, it has to be something like that to do a boost, but... okay, didn't realize that was quite how that was going to work. So how do we decide the inductor value? Inductor selection. V out. Okay. Inductor values between 2.2 microhenries and 10 microhenries. The peak current of the to calculate the current in the worst case, use the minimum input voltage and maximum output voltage and the maximum load current of the application. Right. So in is going to be like 5 volts. Out is going to be 8.4 volts, and then the current is going to be 2 amps. Oof, I could see this being bad. All right. So the top number, V out times I out. So 8.4 times 2 equals 16.8. And the bottom number, V in, which is 5 times 0.84. So 16.8 divided by 4 equals... That was not right at all. Okay. 16.8 divided by 4 is 4.2. So we want to use an inductor that's 4.2 microhenries. Okay. So we go over here, digikey again, and find an inductor. Fixed inductors, 117,000 items. We say 4.2. I wonder how easy of a value that is to get. I also don't know what the maximum like output current to this device is. Maybe I should plan for that instead. Don't know that it knows either, though. If there is a V out max. Or an I out, sorry. Because I think it has to do more with the power conversion. ISW maybe? Yeah, I don't know if it has that listed. Okay. That's all right. So we said 4.2. Nine remaining. Let's give it a shot. What do these look like? Ooh, wow. These are sizable parts. Well, any of them would be fine. Just gotta figure out how to solder them. Something like this would probably be the easiest to solder. That's probably expensive though. Yep. Anything that looks weird is usually really expensive. Engineering pro tip. Also, I'd have no idea if any of these would be even in Circuit Maker, so. Well, let's try one. Let's just start looking through. Yep, that's not. I'm just looking through the easy ones first, the ones that are cheap and would be not too hard to solder. The fact that all these random parts are showing up must mean that they're pulling from a database somewhere that somebody has already put together. All right, let's organize these by price and just start going through the list. Tried that one. That one's going to be too hard to solder. That's going to be too hard to solder. Let's try this one. No model. Just gonna gradually get more expensive, I guess, until we find one with a model. I don't think any of these will, though. These are kind of really uncommon parts. This one does. Jeez. Okay. It's $4, though. At least here on DigiKey. It's kind of a lot. Look at the data sheets here to see if they have a high current inductor. Didn't know if they had a typical application like for power devices or. Gotta be careful using big stuff like this too. It'll be hard to make things fit. All right, let's look at this data sheet again. Just want to make sure that there's nothing else I'm missing for choosing this. Here we go. Use equation 2 to equation 4 to calculate the peak current of the application inductor. To calculate the current in the worst case, use the minimum input voltage. So that's the worst case. Well, this one I've picked. Okay. I probably didn't do enough math here, actually. Oh, wait. Yeah, I definitely did this wrong. Okay. Calculate the peak current of the application inductor. So that value that I got before, the 4.2, was the peak current of the inductor. So then that probably has to get subbed into an equation down here. Yep, to calculate the total peak current. And L is the inductor value. So as long as I pick something in this range. Okay. All right, this is going to become a whole thing, and I'm getting close to the end here. So I may not do this one just yet, but we need to make sure we add it. In the meantime, and maybe that means this. Maybe this means too that we can pick some. Let me look at this actually real quick since we have a half a second. See if there's anything in that range that would give us not this crazy package type. Inductance. And what did they say was the intended? Hold on. .2 to 10 microhenries. Okay. So if I start with that, just give me every value in that range. And we'll see if there's anything that's not horrendous, like anything that's more of a standard package. Yeah, something like this. Okay. 0.7 microhenries. All right, yeah, we can make this work. These would be a lot easier to mount, and they're really cheap too. Jeez. Oh, but these are all maybe something with cut tape. Okay, yeah, 10 cents starting. Okay, so we'll have to go through and do the math next time to figure that out. All right, I'm going to call it here for tonight because I'm getting tired. And obviously, it really feels like we did not get very much done at all because we hardly made a dent into the first. We almost done with the first block, of our big diagram here. We've just literally just this one thing. So, yeah, we got a long way to go. All these circuits together are going to get very complicated, and there's going to be so much to consider. All right, well, not the end of the world. We're making progress. We'll keep making progress, and we'll just keep going and going and going and going and going. Thank you all for joining me tonight. I appreciate your patience and sticking around. And I will see you all later.